So thank you for your attendance, and thank you for this kind invitation in the uncertainty hybrid quantitative hybrid seminar. So I have the pleasure to present you today joint work with my PhD student, Mona Benderwish, that she worked on a kind of interpolated drift implicit Euler multi-level Monte Carlo method, and we applied for diffusions like CIR and CEV models that, of course, do not have the Lipschitz continuity condition on some of their coefficients. So let me first introduce the Euler multi-level Monte Carlo scheme here. So this is our general setting of the general setting of the talk. So I'm interested in practice if you are interested in pricing what we call barrier option. So we have a kind of the payoff function f that depends on the value of your asset price at the terminal time capital T, but you have a term which is given by this indicator where you have a running infimum or running maximum for the whole path between 0 and t of your asset price. And of course, this may kill the option if your buyer is, for example, less than the infimum of your asset price is less than the buyer, or in this case, for the up and out option, if the supremum of the buyer is, for example, larger than a given the supremum of the asset price is larger than a given buyer, then this kills the payoff. So those are called, in practice, exotic options. And generally, it's quite challenging to try pricing such options and having in order, because if you have, for example, to approximate the process X using a numerical scheme, so there is a bias. And of course, this indicator is not smooth enough to deal, to use classical tools for or numerical methods. So that's why it's a bit challenging. And especially the challenge come from the indicator and together with the running infimum or the running supremum. So for me, the XT process is a standard diffusion process where I have a drift. The coefficient drift is called B here, and the diffusion drift is called sigma. And I'm assuming that the coefficient sigma is locally Lipschitz function, so that 1 over sigma is locally integrable, so that I can, of course, here use what we call the Lamperti transformation. So once you apply the Lamperti transformation, you simply need to apply the Ito formula for this function phi, and you find new dynamics now if you work on the Lamperti space. So dyt now has, which is given by phi of xt, has new dynamics where in the drift now appears a function L. You can, of course, here write L in terms of the original coefficients of the diffusion B, the diffusion X. So that's why we have here the coefficient B and sigma, and that's why we need several assumptions on our coefficient function here, diffusion function sigma, in order to make the Lamperti Lamperti transform works. So assume that we start from a diffusion that I'm able to transform in this way. So this, of course, has many advantages because now the noise is additive. And when the noise is additive, a lot of properties, of course, of the Brownian motion can be, we can take advantage of a lot of formulas associated to the Brownian motion. However, when I have a multiplicative noise like here, so of course, several tools or several formulas connected to the Brownian motion, we cannot apply them with a multiplicative noise. So this is our main motivation. And now, starting from your original problem for pricing the barrier option on the X space, now you move your pricing problem to the Y space. So if you do that, so then the down and out and the up and out options becomes as follows. So here you have a new payoff function G, Of course, G is, you compose F with phi minus 1, where phi is given by the Lamperti transform. And of course, you transform your barrier, and now you completely move your problem to the Lamperti space. And now we are now dealing with this, the computation, how can we efficiently approximate numerically these two quantities to price the barrier option. Of course, here is the aim. So from now on, I'm assuming this general setting. So keep in mind, so starting from any diffusion, if we are able to apply the Lamperti transform, then we are able to have this form for the diffusion. So this general setting was introduced first by Aurélien Alfonsi in a paper in 2013, where he studied numerical schemes for such kind of class of diffusions. So I'm taking for the moment the same assumption as in Alfonsi paper, so where I have a kind of increasing here property from one side for the drift L. And then this assumption is, of course, ensures by Fuller test, ensures that the stochastic differential equation admits a unique strong solution. And more than that, if we have this property H1 that is satisfied, then we are able to prove that the process Y is strictly positive. So this is an essential part if we keep in mind that later on my application would be for CIR or CEV processes. So I need to have this property for my process. You will see it later why this is important. So this is my the general framework. So this is the diffusions, and we know that it is strictly positive. And we want to conceive numerical schemes to approximate the price of the barrier option. So in his original paper, Alfonsi introduced what he called the drift implicit Euler scheme. So the drift implicit Euler scheme, as he has here additive noise, so the implicit appears only on the drift, so that's why it's called drift implicit. And this is the interpolation he considered for any t belonging to the interval of between two discretization points. So, and he was able to prove that the scheme is well defined. Actually, he proved under the assumption that I showed you above, that the process, the approximation is itself strictly positive. And this is a nice feature for what we are going to show later on. And moreover, he assumes that the derivative of the drift and the second derivative have several properties here, finite moments given by the assumption H2. And under this assumption H2, Alfonsi was able to prove that the scheme here, the y hat nt, has a strong error of order 1, and also the scheme is strictly positive. So starting from this result, in our study, we introduced a slightly modified drift interpolation for the drift implicit Euler scheme. So our interpolation is as follows. So we start from the discrete scheme is defined in the same way as Alfonsi. So here you have the y bar n ti plus 1, and in the drift you keep the same component. And however, for any t between ti and ti plus 1, between two time discretization points, we still freeze the drift at point ti plus 1. So here at this discretization. So if you compare it with Alfonsi, he put it y bar and t here. So our interpolation is a bit different. Why we need to change this interpolation? Because we have in mind to price barrier option to apply with the known or the popular technique in quantitative finance of the Brownian interpolation. and that one we need that the drift is somehow frozen at the discretization points. This I will explain this more in details later on. So for this slightly different interpolation scheme, we've been able by here strengthening a bit assumption H2. So under assumption H2 and assumption H3, we are able to prove that our interpolation scheme here satisfies, for n large enough, satisfies a strong rate of convergence of order 1, 2. And of course, as a corollary, if we now have the moments of y, and if you have a control of the strong error, of course, you have a control of the moments of your scheme. And this is essential for our study later on, but we have also to strengthen a bit the assumption on the drift in order to satisfy this last property. So once the scheme is studied, so now let's go back to our aim, which is the pricing of the barrier option. So we have two types of payoff, the down and out and the up and out. So the first thing is we still have equality. So I'm just here writing the indicator of the running infimum or the running maximum on the whole interval 0 capital T. Capital T stands for the final maturity. We can write it as a product of n indicators where I take into account the running infimum for each small interval in my time, discretization time. And then I replace here the yt by the true process, by its approximation using the new interpolation that I just presented above for both schemes. So now I'm interested to run Monte Carlo, or more precisely multilevel Monte Carlo, when dealing with these two kinds of payoffs. So in the literature, there are a very well-known property, the popular in quantitative finance, that may, using kind of tower property, apply it several times, we are able to prove that this payoff here can have a newer representation where we replace it, the product of this indicator, by the probability here, by some probabilities given explicitly given here, where you can see that the q bar I here are exponentials measuring whether or not the process is larger than the barrier D or smaller than the barrier D. So, and the same thing happens for the up and out. So these techniques, up to my knowledge, I think the oldest paper I found in the literature is the one by Baldi, 95, and there is a nice paper by Ahmed Kebaier, 2009, where there is a complete survey and also related refinements on these techniques and applied also in the context of quantitative finance. So the proof of, yes.
Interesting. Does this probability relate to the excursion probability for the process as such?
So, sorry, I didn't get the question.
So the probability written here, it
Yes.
looks similar to the excursion probability for the Brownian motion.
Yes, exactly, because since in the process y, you're right, since the y bar here, there is an additive noise, right? So if you go back to the scheme, yes, so there is this additive noise. So essentially what you can do is you can kill the drift using a kind of Girsanov transform. And then the law or the distribution you have to treat is only dealing, the supremum is now only dealing with, so if you have to look to the interpolation, sorry, is only dealing on the WT. And this is, as you said, is exactly given by this exponential. So that's why you recognize these probabilities that are connected to the supremum or infimum of the Brownian motion to hit a barrier, a given barrier. That's right.
Thank you. Yeah, sorry for the interruption.
Welcome. So, okay, so now this we have this new representation, and the advantage of this representation is, of course, that we get rid of the indicator here. So we have now a better, so a smoother function, which is given now by this 1 minus the exponentials you see here. And of course, the other advantage, I didn't say it because it's quite intuitive. Of course, if you proceed in a crude way, what can they do? They simply approximate the infimum, the continuous infimum or the continuous supremum by the discrete version, right? But if you consider the discrete version, you only consider the maximum of the process only at the discretization points. So you may miss the information between two consecutive discretization points. Means that you may observe that your scheme is above the barrier at the discretization points here, ti at ti plus 1, but you have no information. It may, your process may be smaller than the barrier in between the 2 points. So that's why, of course, now using this probability, we take into account of the behavior of the process between two discretization points. So until now, from this approximation to this one, there is no additional bias.
Ahmed.
Yes.
Numerically, also one can say that if you don't do this sort of tower property and apply, like you said, this as is, you get the square root of delta t rate of convergence, right?
Exactly.
Whereas if you do this, actually you recover delta t, and that's a big deal, right? To
exactly.
go from half to
exactly. Exactly. This is the aim why we move to this smoother function, because as said Raoul, we want to take have a strong rate of convergence for the product part here. And if we did it with the indicator, of course, we immediately lose this rate. Thank you. So now let us see how to combine this interpolated drift implicit Euler MLMC method with the multilevel. So here I was inspired by Mike Giles' works that already looked to this problem for the barrier pricing barrier option. And let me present briefly what is the aim here. So we first consider, let's fix, for example, the finest level in my Monte Carlo given by 2. So n corresponds to 2 power minus capital L. So L is given by this expression, and the n is the level I wanted the number here, or the number of time step here that I want to use in my numerical scheme. So let me fix capital L and then start conceive scheme that is refined when L moves from 0 to capital L. So now I have a new size here of step given by HL, and as L moves from 0 to capital L, my scheme becomes here, y bar 2 to the power L, becomes finer and finer, so more precise, okay? So intuitively, what you have to do is simply you write for a given fixed small L here, you write the payoff, and then you split, right? So this is a telescoping sum. So of course you did nothing. Your quantity of interest fixed at capital L can be split as follows. So you have essentially capital L plus 1 expectation. Of course, there is here is the crude approximation, and then you have some corrections coming from this expectation. So this is mainly the idea behind the multi-level Monte Carlo method. And you can proceed in the same way for the up and out, for the down out, sorry. And here, using the proposition from the Brownian bridge technique, you may rewrite your payoff for the finer here, for the finer level. You may rewrite it in terms of the probabilities of the Brownian motion that hits or not the barrier. So this is for the finer level. It's quite simple. However, the tricky thing starts in the coarse level, because in the multi-level Monte Carlo, the essential thing, in order that these corrections do not be, of course, time consuming, we expect that both quantities have somehow slow, very, very small variance, and they should, and the one have to find a kind of coupling between the coarse and the finer scheme. So they have to be built on the same path, Brownian path. And if you proceed also in a naive way, you may also lose the optimal rate in this case. However, Mike proposed in 2019 a very nice idea, is that when you apply your Brownian bridge technique for the coarse level, so here I'm in the coarse level, it's indexed by L-1. So then you have to consider the tower property, not only with the two bounds on the coarse grid, but you have to include the value of the process in between. So you have the coarse grid here, you have 2 points, and you have 1 point in between, which belongs to the finer grid. So Mike proposed here to condition here with respect to the scheme evaluated on this. This point belongs to the finer grid, right? So we have a 3 points conditioning here, expectation. And if you proceed in the same way as for the classical case, so you proceed with the Girsanov transform and then change of measure, and then use the property of the Brownian motion, the density of the supremum or infimum of the Brownian motion to hit the barrier. So if you define quite precisely your interpolation here for the core scheme, then things may be better than the naive scheme. So, and it turns out that our interpolation scheme works here. So for the course, we propose to use our interpolation that I presented in the first part of the talk. So if you proceed in this way, then, so this is the new property. So now I get here, so this is the drift part. And thanks to a Girsanov change of variable, I can get rid of this drift part. And now the supremum only concerns the Brownian motion. And now, so I'm able to treat the two indicator, not on the coarse interval, but on the two pieces in which I can see here the points that belongs to the finest grid. So thanks to this trick, then your initial product that runs for indices on the coarse grid is a product of two probabilities. Okay, there's two quantities, and this is behaves better numerically. So and then even for the theoretical proof, this allows you to rewrite the payoff of the core scheme using here a new increment, not increment, a new here index I that runs on the finest grid, because we have two probabilities here. We have two terms for each product. So of course I can rewrite it as a product of 2 power L terms. And this is essential for the proofs. Why? Because if you now want to compare the coarse approximation, so the coarse approximation now appears a product that runs from 0 to 2 power L minus 1. And if you go back and you want to compare it to the finest, where is it? To the finer approximation here. So you will see that you would have 2 to the power L minus 1. So it's I have two quantities that runs on the same in this range of index. So also it helps for the mathematical proofs. So once I fixed the finer approximation, the coarse approximation, and both are built on the same path, we can easily check that there is no bias between them, so that the telescoping properties still works for this estimator. I can similarly conceive the same multi-level estimator for the down and out barrier option. And here, of course, I simply replaced the expectation in the above telescoping sum by empirical means. And the idea of the multi-level is to, of course, to have here very large for the coarse scheme, which is not the scheme is very, I mean, not time consuming. You can allow yourself to have large paths here of Monte Carlo. And once your scheme becomes smaller and finer and finer, of course, you have to decrease, to decrease the sample path here. Now, if we want to study the multi-level Monte Carlo behavior, one needs, of course, to know what happens for the variance of the estimator, and this is the main the crucial point in the multi-level estimator. If we are able to quantify the variance of the terms here, the corrections terms, then it's okay. We know the regime in which the multi-level Monte Carlo will run. To do so, here, inspired by Mike Giles' paper. So actually, I have to say a word on Mike's work. So in his work, the diffusion is that he considered a diffusion with smooth coefficients. I mean, globally Lipschitz coefficients. So and also he used a Milstein scheme for the approximation scheme. And in my case, I didn't have this property, the global Lipschitz property for sigma now. So keep in mind for my application, I would apply this to Cox-Ingersoll-Ross process and to the CEV process. So of course, this is not does not satisfy the global Lipschitz condition for the diffusion coefficients. So that's why we have to reconsider. I mean the tools that allows Mike to prove. I mean to get the optimal the study of the variance of the associated multi-level Monte Carlo method. So in our case, we have to study this extreme path. So this extreme path tells you what is the probability of your process or the approximating scheme, or the error between the process, the approximating scheme, or even between the coarse and the approximation scheme and the finer approximation scheme. How do they behave? What is the probability of these schemes if they are larger than some threshold here that may go to infinity? So that's why we call them the extreme path. And in the case of Lipschitz coefficient sigma, we can prove that these quantities, this extreme event, are as small as we want without any condition. So this is what Mike did in his work. He know that this extreme path for a diffusion with regular coefficients, this can be as small as we want without any condition. However, in our case, I have to strengthen my assumption on the drift L, and I'm able to prove that these quantities are smaller as I want, but not as without. So I have to pay something here. So what I'm saying, so if I assume that my assumptions on the drift are satisfied for some p, for a given p, okay, larger than 1, then this cannot be smaller than p times eta, where the eta is the power of the threshold I fixed here. Okay, so I have a restriction. Of course, if you know that your sigma your coefficients are globally Lipschitz, you don't have any restriction anymore on the Q here. So I have to take into account this first constraint if I want to use, of course, this lemma. And now we come to the main, one of the first main result of this work. So if we assume that G is kind of locally Lipschitz function, so I may allow myself to have positive here power here. Of course, you can assume that it is Lipschitz, but we can also allows ourselves to have power here, positive power, and also if I assume that g of x is polynomial linear growth. So taking into consideration my previous assumption on the drift L with some power p that is larger than this level for some delta between 0 and 1/2, and for HL, HL is the time step, right? For a given level in the Monte Carlo, that is sufficiently small, if additionally I assume that the infimum of the process, or respectively the supremum of the process, has a bounded density in the neighborhood of the barrier, then the multi-level estimator that I presented above has the following variance order. So the variance between the finer and the coarser behaves like big O of the time step power 1 plus delta. And same thing for up and out option. So the variance is big O of the time step power 1 plus delta, where delta is positive here, between 0 and 1/2. Okay, so this results, of course, under some restriction. Of course, if you are dealing with so I will say a few remarks before moving to the sketch of the proof of this results. So if you combine this result with the well-known complexity theorem in the seminal paper of Giles 2008, so we deduce that for any delta between 0 and 1/2, the MLMC estimator Q bar D and P bar U reach the optimal time complexity big O epsilon minus 1 for a given precision epsilon. So it is in the theorem, the complexity theorem, there are three cases. The case where the power of the rate here for the convergence of the variance, if the power here is strictly larger than 1, then it says that the time complexity of the multi-level Monte Carlo is epsilon minus 2 if, of course, you want to achieve a total precision of order epsilon. And of course, if it is equal to 1, then you have another convergence regime, complexity regime, which is epsilon minus 2 log of epsilon power minus 2. And of course, if it is smaller than 1, then you are in the worst one, the worst regime. So since here we have a variance that have a rate of convergence that is strictly larger than 1, so we are sure that the multi-level Monte Carlo method will achieve the optimal time complexity that it can reach, so epsilon minus 2. So if you think in terms of classical Monte Carlo, and if you fix a total precision of order epsilon, it's like you are running an unbiased Monte Carlo estimator. So it's like you don't have any bias, despite the fact that, of course, in your MLMC, there is an approximation scheme, right? And this is very interesting from a practical point of view. Now, the other remark we can do is, of course, one may choose delta close to 1/2. If you choose delta close to 1/2, then you reach an optimal rate, which is here 3/2. And however, the constraint here on your moments P may explode. So if you take delta larger, close to 1/2, this is not a good idea because you will have a lot of restriction on the coefficients you are going to deal with in the diffusion or in the numerical part. So that's why we are only asking for a delta strictly positive, but very, very small. So we can reach the 3/2, and of course, in the Giles paper of 2019, he proves that for the barrier option, the variance, when of course the diffusion is Lipschitz, has Lipschitz coefficients, then the variance is order 3/2. So in our case, we cannot allow ourselves to reach this order for the variance, but at least 1 plus delta is enough to achieve the optimal rate for the optimal time complexity for the multilevel. Now, let me give you a sketch of the proof. So the idea is as follows. We split in 3 events. In the first event, called A1, we consider any of the extreme paths I presented in the above lemma. So I'm working in this if one of this extreme path is satisfied. Okay. And using Cauchy-Schwarz lemma, and thanks to the property on my payoff, and using also my lemma, which gives me the probability of this events, or an upper bound for the probability of this events, that behaves as h power q. So since I have the square root, and here I have q half, but I need here to take into consideration the restriction I have. So Q cannot be as small as I want. It is limited by this P eta, where P is the natural, appears naturally in my assumptions of the finite moment of my drift and its derivatives. And now, so this is the first event. So the complementary is all the extreme paths. I'm not on the extreme path event. So all of them are not satisfied. And I split this second big event into 2 events, so A2 and A3. In A2, I consider the case where the infimum of the barrier minus D is larger than this threshold. So in this case, we can measure how close we are to the barrier. And thanks to the rates, since we are in the non-extreme path, I can control the distance between the scheme and the true diffusion, or between the finer or the coarse scheme, precisely because it's given by the rate I have here. So we are able to prove that here the variance on the second event behaves with this rate. And finally, the third event is the complementary of this third event, where I have to deal with the difference between the products, and here the nice properties of the scheme, together with the condition that I have a bounded density for the infimum of the process. We are able to find this upper bound for the variance of the third event. So as you can see, I have 3 upper bounds. This one for A3, this one for A2, this one for A1, and I have to choose all the other parameters in optimal way, such that the total variance, all of the 3, are of order 1 plus delta. And it turns out that for this choice of eta, and I fixed also epsilon equal to delta, we can find that all the 3 events achieve the order h for the variance, of course, h to the power 1 plus delta. And of course, you have to have all this constraints work together. We need this final assumption. So this is standard calculation that of course allows you to obtain what is the lower bound for P. Now let's see how we may apply this in a concrete case. For example, assume that I'm dealing with a Cox-Ingersoll-Ross model, and I'm trying to price barrier option on this model. So at first, so this is the dynamic of a Cox-Ingersoll-Ross process, where you see here in the sigma, I have, of course, the famous square root of x coefficient. I'm here considering the Euler condition to avoid, so that my process is strictly positive. Then I can apply the Lamperti transformation with So it's simply applying Ito formula to square root of xt. And now I have my new dynamics, and this is the drift. So in the drift, you can see I have the coefficient here constant over y minus constant or plus constant time y. So this is maybe the most challenging part we have to deal with. Now your payoff changes, of course, because of your Lamperti transformation. So it is your call option, for example, if you consider a call or a put, composed with x square function. And here for the Cox-Ingersoll-Ross process, we want to see whether or not our conditions are satisfied and which conditions this assumption are satisfied. So it turns out that our assumptions are satisfied. So I'm taking into account all the moments for the different derivatives here of the drift, together with my new assumptions on the drift, and combining this with known properties on the Cox-Ingersoll-Ross process. So I'm asking that this negative moment is finite. But we know, of course, that I can't have all the negative moments are finite, right? So I'm limited by this lower bound. It's well known. It's well known for the Cox-Ingersoll-Ross. So this gives me one constraint on P. And now taking the other constraint coming from my theorem, so I have to pick up coefficients here, A and sigma, such that I can find a P that is larger than this upper bound, lower bound, and smaller than this upper bound. And here a lower bound for this P, since I know that delta is between 0 and 1/2 is 18. So it lets you know that, of course, it's a very, in terms of theoretical application. So if I want to check my theoretical arguments, this is very constraining, right? Because here my coefficients, I'm asking that A over sigma square is larger than 18 times T4. So, and more than that, if you want to apply the previous theorem, you have also, you need the additional assumption is that the infimum of your process or the supremum of your process has a bounded density in the neighborhood of the barrier. So this, I was curious about this, so I thought that this kind of result would exist in the literature, but it was a bit surprising. There is no, I didn't find at least papers that treated this problem. However, there are existing results that helps you to prove this result. So let me introduce the confluent hypergeometric function 1f1 here, given by this infinite series, and the result we prove here is that if I denote xt the CR process, then the supremum of xt has continuous density on any compact set K that belongs to here the initial point of your process, so to the interval x0 plus infinity. And also we've been able to give a semi-explicit expression for that density. Of course, we proved that it is continuous. And here, the phi hat can be expressed in terms of this confluent hypergeometric function. The same thing for the running minimum. For the running minimum, and now I'm introduced this trichomy confluent hypergeometric function U that also can be expressed in terms of the confluent one. And there is a nice paper by Xu and Lin of 2006 where they have explicit Laplace transform of the heating time of a given barrier Z if you allow your process starting from a point that is initial point that is larger than the barrier. Then you have explicit Laplace transform. And thanks to this Laplace transform, we are able to have a semi-explicit expression for the cumulative distribution function of the continuous running minimum or infimum, and then proving that we have the right to, of course, to consider derivative inside the integral. We computed the derivative of the cumulative distribution function, and then we get the density with also that is expressed in terms of this integrals but with integrand that are finite and that we perfectly know the behavior at the neighborhood of the plus infinity and minus infinity. So let us move to the numerical tests. So for the numerical test, I consider the call option here. So by Lamperti transform, of course, my payoff becomes like this. So I have to compose with the x square. I consider the interpolation of the drift implicit scheme. So it is given in this case by this recursion. And here the thing here is that I'm to solve to implement my scheme, I don't need any root finding algorithm because I know that this has explicit expression. I mean, you may solve it here because the drift is 1 over y, and here you have constant over y plus a constant times y. So you may find the solution of this equation, and of course this is strictly positive. So there is no additional cost to solve the implicit interpolated drift here scheme. So in the literature, there is a paper by Davidov and Linsky, 2001, where they considered barrier option on Cox-Ingersoll-Ross process, and they used kind of semi-analytic formulas, not Monte Carlo, to approximate the price. So we find somehow benchmark prices. So we consider the same set of parameters that they considered, and we tested both. So I mean both up and out and down and out options. So as you can see here in the table, if you ask for a precision of 10 minus 3, the price is close to the benchmark one, and the multi-level Monte Carlo cost is this given by this number, and the saving between the multi-level Monte Carlo cost and the Monte Carlo cost is about a factor of 2060. So we proceed in the same way for the complexity of the up and out the barrier option. So the saving between the Monte Carlo for an accuracy of order 10 minus 3 is 90 in this case. And here we plot the usuals curves here, where you plot epsilon square times the cost of your method versus the accuracy, the epsilon you want to choose. And here, as you can see, the red curve is for the multi-level Monte Carlo, so it is flat. So means that the cost of your multi-level Monte Carlo is really epsilon minus 2. However, as you can see, the cost of the Monte Carlo one is increasing. So this, of course, would behave like epsilon minus 3 in this case. And the same thing happens for the up and out barrier option. The second and final application is to the CEV process solution to this model. So in this model, instead of have square root, you have a power alpha, and there are several ways to choose the alpha. So in the literature, many people essentially in finance, alpha belongs to 1/2 1. So if you choose alpha between 1/2 1, your CEV process, your CEV model, you can't guarantee here the positivity of your process, so it may hit 0. So that's a bit annoying for me when I want to apply Lamperti formula. The idea is, maybe I will discuss alternative ideas, but let me present what I did in this case. To avoid that problem, I considered the case where alpha is larger than 1. So in the case alpha larger than 1, this was proven that by Marchior that this process remains positive, strictly positive. And then I can apply of course my Lamperti transform. So once I apply my Lamperti transform with this function power 1 minus alpha, and now I get this new dynamics on the Lamperti space, where you have this new drift that looks quite similar, right, to the Cox-Ingersoll-Ross process, despite the fact that I had a power alpha here. So now the pricing problem moves from the X space to the Y space, where now I take into account my change of my changed payoff. So here, in order to satisfy the condition, we need to prove kind of a corollary of the, so those are the moments that I need, but I need here a corollary for the CEV process. So because for the CEV process, as you can see, if you apply to the pay of G, the power here may be negative. And if this power is negative, so of course this should of course take into account a new result. But we've been able to prove that even though we have this behavior for my payoff function G, then the things work for P between this lower bound and this upper bound. So in other terms, I have to choose here alpha very, very small if I want to all my assumption to be satisfied. As you can see, very small and close to 1. And also the other alternative idea that exists in the literature, if you consider alpha between 1/2 and 1, is that you may consider a positive drift here. And now you are sure that your diffusion is strictly positive. However, if I consider such diffusion, I'm not able to prove, like for the CIR case, that this infimum has a continuous density in the neighborhood of the barrier. The same thing also for the supremum, running supremum. I'm not able to prove that it has a continuous density in the neighborhood of the barrier. So this remains a challenging problem. So that's why I considered the case where alpha is larger than 1 and I don't have a constant drift here. And for this case,
just a question. Can I ask a question?
Yes, sure.
Yeah. So if alpha is tiny, then it would be very difficult to ensure that the process does not cross 0, right?
If alpha is close to 1?
No, even close to 0. I mean, smaller than 1.
Yes.
That's what complicates the life when you have an alpha small, right?
Yes, exactly. Except if you put, of course, a positive A here, right? If you include a positive A here, positive constant, then you are able to prove the positivity of the process.
But even if alpha is less than 1/2?
No. I don't know a proof for alpha less than 1/2. You're right. Yes. For alpha, yes. It's a bit.
You don't know anything for alpha less than 1/2, right?
Yeah, I don't have in mind any proof that deals with this case. Yes, you're right.
Okay, thank you.
Welcome. So let us go back now to the case A equals 0 and alpha larger than 1. So the process remains positive and my Lamperti transform works. And more than that, in the book of Jean-Blanc, Yor, and Chenet, 2009, we have explicit Laplace transform of the heating times. So here the first heating time of the diffusion, the CEV process that hits the barrier Z when it starts from initial point that is lower than the barrier is explicit in terms of this spatial functions. And of course, if you know the Laplace transform, then you have access to the cumulative distribution function of the running supremum. And once you have written in a semi-explicit way the cumulative distribution function, and if you justify, of course, convergence dominate conditions, you may compute the derivative inside the integral and then prove that the quantity you obtain is positive. So here we obtain semi-explicit formula for the density of the CUV process, and we know explicitly the phi hat in terms of this special function. And in the same book, we have also for the running minimum, we know that the Laplace transform of the heating time of the barrier Z of course, the hitting time of the process of a given barrier Z when you start from an initial point that is above the barrier is explicit and also that can be expressed in terms of this Whittaker function that we know it's classical. We know their behavior, so we are able to now, thanks to convergence dominate kind of theorem, we prove that the density is explicitly given, semi-explicitly given by this formula, where we have explicitly the psi hat expressed in terms of our special function. So now, in terms of practical implementation, so I applied the Lamperti transform. So this is the drift I get, and of course here I don't have any root finding to implement. So algorithm to implement. So this solution can be expressed explicitly, and I tested with even alpha, which is larger than my theoretical assumption. Here alpha equal to 1.2, and I applied to this payoff. So in this case, we didn't have a benchmark, but we find very satisfactory results. For example, for the accuracy of order 10⁻⁴, the saving may reach 8,900 a factor of equal to 8,000. And for the down and out, the saving for a precision equal to 5 times 10⁻⁴ is about 2,500. So if I have now the famous plots where here the figures shows the epsilon square times the cost versus the epsilon, your accuracy, you can see it's perfectly flat in terms of multi-level Monte Carlo method. So it means that this is exactly epsilon -2. However, of course, it is increasing for the Monte Carlo case. So the paper is available on arXiv, and thank you for your attention.